Adrij Banik from Central University of Jharkhand, and recently I was working on my research paper for experimental demonstration of delta potential, scattering matrix, and various potential types of 1 by r, 1 by r square, 1 by r cube, 1 by r to the power 4. So how to simulate this type of potential in IBM quantum experience I did, which I was going to present in this video. So hope you will like this. And we started with, let's first do the introduction. So basically, why we use quantum computers for this simulation? We can use classical computers too, but to enhance the efficiency, quantum computers, as quantum computers we know that it works on qubits, which is basically not 0 and 1, it's the superposition 2. So for simulation of a quantum system by using quantum computers, this becomes the advantage of getting an efficient result rather than a classical computer. So here we chosen the quantum computer. And so from beginning the simulation, what we did, we know any quantum system having potentials. Let some potential is V. So how we simulate potential V? We usually in pen paper 2 we use that as Schrodinger equation, general Schrodinger equation, E psi equals to H psi, where when this equation is further carrying on this equation by it's taking its double derivative dt square by x, we use V as a potential, both term. And here in terms of V, we will change how delta potential will be put on this place, how scattering potential, and how the potential of the term of 1 by r and 1 by r square, 1 by r cube, everything. So here we will show how we did this. Our Schrodinger equation, IH cross del del T of psi x T of this and x psi. Here this is our Hamiltonian, so which can be written as S naught Ex. Now, so the potential term in the Schrodinger equation only containing this Hamiltonian contains the potential term. So it will become very simple if we decompose this Hamiltonian and goes on simulating the whole Schrodinger equation. The big question is that how Schrodinger equation will be converted into such software thing like quantum computer, which we are doing in IBM quantum experience. How a Schrodinger equation can be put into this? So here we chosen that we will decompose this Hamiltonian in terms of quantum Fourier transform. Okay, quantum Fourier transform and quantum Fourier inverse transform, which is in quantum computers, quantum Fourier transform and Fourier inverse transform, we can get this easily by using some Hadamard gate and U1 controlled phase gate. So now how we implement this in a quantum computer? We are showing that if this Schrodinger equation is integrated from some t equals to t2, t equals to t plus delta t. If we integrate this, we will get a result E equals e to the power minus I h cross plus Vx to delta t into psi xt of course. By integrating this side, this sign from t to t plus delta t, we are getting this result. Now here we will separate these terms and we will use these terms as a gates in quantum computers. So separating these terms, like E minus I h cross h naught plus V x delta x. There is a very famous decomposition rule which is called Suzuki-Total decomposition rule, which shows that a term like e to the power I h cross h naught plus Vx into delta t can be written as e to the power minus I by h cross h naught delta t into e to the power minus h cross Vx delta t. Now what's so uncommon in this? It's we can say that it's a simple just e to the power something a plus b can be written in the form of e to the power a into e to the power b, but it's not that simple. Here h naught and Vx is a matrix, not a number or any quantity. It's a matrix. So this is known as Suzuki total decomposition rule. Now here we get these two terms h naught and Vx separately, so we can use this in our next exercise.
The actual rule is the following: e power a, e power b. All right. This thing can be written as e power a, e power b into e power minus half the commutator of ab only when a and b's commutator is not 0, but a with ab's commutator's whole commutator and commutator of b with the commutator of ab, this thing is. So when he means this thing, which is otherwise e power I h cross h naught and I by h cross Vx, then you have to take this as A, this as B and satisfy this condition first, and then only you can apply the Suzuki total.
So there is another Trotter decomposition. So are they same, Suzuki Trotter and Trotter, or there is some
Total,
because
there
Trotter
would
is
be-
similar, like
Yeah,
this commutation should not be equal to 0. When they are 0, then only this rule applies. So that's what I'm asking.
they could be perhaps derivable from each other
Okay.
based on different conditions. Otherwise, both are meant to the operator exponential decomposition.
Now here e to the power minus I by h cross h naught delta t. In when we implement these terms in quantum computer, we will use this relation QFT inverse e to the power minus I by cross c square by 2m delta t QFT. So this h naught obviously e to the power minus I by h cross h naught delta t consists of QFT inverse and we can write this as components of this, where this is the kinetic energy operator. I mean this P square 2m is the kinetic energy term. Okay, so we get here the kinetic energy term, obviously the potential energy term, and we can write use QFT inverse and QFT for simulation of our initial Schrodinger equation, which we write as psi x t2 t plus delta t after integration.
This is a standard result that you are borrowing, right?
Yeah. It is we borrowed it from the reference of some earlier works which I have done.
Okay.
So the initial Hamiltonian, initial Schrodinger equation, wave equation, which we are going to simulate, is x t plus delta t plus t inverse to the power minus I QFT times e to the power minus I by h cross Vx delta t. These are the major equation which we use going to simulate. Which we are going to simulate by changing in this term Vx. We will put for delta potential, we will put alpha delta x. For scattering potential, which we know as the scattering matrix varies. For a scattering matrix is generally angle dependent. Implement QFT inverse as I get e to the power minus IH cross p square by 2m delta t as I get.
Okay. And
QFT as I get.
Okay.
This potential term as I get.
Okay, all right.
So next we will just show that how potential Vx, for delta potential we can write Vx is a function of delta x for delta potential. For scattering matrix we will use some potential which will be 4 angle dependent, theta 1, theta 2, theta 3. For V, some potential type like V1 by r square, which is a type of potential V1 by r square, V in terms of 1 by r cube, V in terms of 1 by r to the power 4. We construct the gate and we will put these potential terms in place of this, and by simulating this whole equation we will get the result, and which will satisfy with the theoretical result. So for this kind of potential we use it for two particle interaction, and when we use two particle interaction, these are for single particles, delta function and scattering matrix. But when we use these r square, r cube, r to the power 4 terms, we are using it for two particle interaction. So next she will continue.
Hello, myself Khyati Supriya, and I'll continue. As he said that these 4 terms are implemented as a gate. So now I will tell you how quantum inverse quantum Fourier transformation, quantum Fourier transformation, and this kinetic energy part, potential energy part is implemented. For the inverse quantum Fourier transform, we use 2 Hadamard gates and one controlled phase gate. For 2-qubit system, Fourier quantum transform. We use two Hadamard gates and one control phase gate. Here the angle will vary. In general, the inverse quantum transform will vary like in every qubit. Two Hadamards will increase and one phase gate will increase. Just like for 3 qubit, if I show you. This way. For 3 qubit, as E part means there, as Adrij told, the kinetic energy part was like p square minus I by h cross p square by 2m delta t. For momentum, we are going to implement the gate as pi 01 means qubit. It is also representing the qubit. Here is e to the power minus I gamma for 0 qubit. These 3 parts are referred to Noren's paper or Gaurav's paper. Noren's or Gaurav, I don't remember. From where we are, and delta t for delta potential, we took delta t as 0.01. For scattering matrix means 0.01, not delta t is equals, yes, delta t equals 0.01 means 1 by 100, means that we had 100 times iteration of the same circuit, means we constructed one circuit for delta. This was for kinetic energy. For potential energy, we noted as P. We made the circuit for this. There was anti-control phase gate, and here we took any angle theta. We actually did this performance for different angles. At particular angle, that was 11 pi by 12. At that point, we got the best result for 11 pi by 12. This anti-control, using anti-control for we obtained a matrix for D, we obtained a matrix for everything. Here we means for this potential energy, if we choose a particular state 01, means we have a potential only at this state. We should potential at only this state. Another term should be 1 like this. We got a diagonal matrix. Using this matrix, we constructed the gate for potential energy. Similarly, we we obtained the matrix for this also. One state, 1 0 state, and for 1 1 state. Okay. If we here we have considered that we should find that spike at in particular state. That is here we considered it is in 0 1 state. Okay. Then the potential should be at this position. If it is 4 into 4 matrix, the potential should be in 0 1 state, and in other 3 states it should be 0. From matrix we can get the gates. We can know which gates we have to implement for this circuit. I didn't. This 501 part, from this 501 part we got controlled U1 gate. From Z1 we got RZ gate. From Z0 again we got RZZ, that gate. Using these 3 gates we constructed the circuit for kinetic energy operator. And now from Schoenberger's paper, similarly we took that part and again calculated the matrix and got these gates for each terms, and that part was implemented. Scattering matrix. In scattering matrix, actually, as Adrij made that diagram, here we can see that for 3 here, if we consider the 3 qubit system, means we should have 0 0 states should be 0 0 1 0 0 0 0 0 0 0 1 0 1 0 1 0 0, means we should have 8 states. If there are 4 curves, therefore we consider that we should the probabilities should be get at 4 states. Means we divided these regions in 3 regions. Means this part don't give any probability because their probability of getting particles is very low, means almost 0. We get potential only in this region. So we have calculated for only this region and implemented the circuit for only this region. For this region 1, we assume these are these states for region 1. For region 3, means the curve is dying from this region. This is for region 3. Now we assume that only for these states we have potentials. Thus we assume there is some potentials like theta 1 for these states is like theta 2, theta 3 and theta 4. Here also we implemented that D operator, P operator, but there are 2 particles, means there is kinetic energy, potential energy, and there is also interaction potential also. That we represented as V, perhaps. Vi. That is here these were same as earlier part, but here new thing is interaction potential. We worked on interaction potential in this part.
We constructed our whole system, and when we are implementing this on IBM QV, we are following a program obviously in QSkit. So when this program is run for 100 times, the same program, and we run this program for 100 times, it is which is called the 100 times iteration. If we run it for 2 times, 2 iterations, run it for 3 times, 3 iterations. So here the result what explains that the initially the probability, the histogram seems like the probability of the particular state. These are some states 0, 0, 0, 0, 0, 1, 0, 1, 0, 0. At this particular state is maximum. Where in other state the probability decreases or tending to 0. When after 100 iteration, we run this program for 100 iteration. When after 100 iteration, we see that the probability got distributed. It's not maximum at only one state. It is some probability of getting particle in this state, some are dying, some are in this state. This is the probability distribution. So what we see or what we match by theoretical result, that the particle from this state got tunneled to these states, maybe got tunneled to these states. The result matches with our experimental for that's how the theoretical result shows for delta function potential. This is the delta function potential. This is the scattering matrix. These 1 by r square type, 1 by r cube type, and 1 by r4 type. From theoretical result, theory we know that at a certain point there will be a peak for delta function, but after this point there will be no probability of getting this particle there. So what we got in the result after 100 iteration, we got the result as this is something 0.1, which is very much tending to 0, and so not exactly a theoretical result, but we can see that the probability of the particle at 0, 1 state is 0, 1 state is minimum, which means the probability here is the minimum probability. So it simplifies our. For scattering matrix for 4 angles, we got 4 states for 4 different angles, which shows the probability here at these peaks. For V 1 by r square type term, we got similar type because we don't know exactly what the system is, how the system of V1 by r square will behave. But we calculated if there would be a 1 by r square type of system, 1 by r cube of system, 1 by r to the power 4 of system type of system, the result of after simulating would give something like the tunneling type of this probability got distributed from one state to every state, like from this. Similarly from